Analysis of variance. Here we have more than two populations, and we want to compare their means. And in order to do that, since we in this example we have three populations, we need to do these three comparisons. So we can compare mu1 with mu2, and the alternative hypothesis is that mu1 is not equal to mu2, or we can compare mu1 with mu3, and same way we can compare mu2 to mu3. So these three pairwise comparisons are possible, but that will take a lot of energy. So in order to avoid that, before we do this these pairwise comparisons, we just ask a general question that whether these three means are similar or they are different. And the technique that can answer this question is what we call analysis of variance, or ANOVA. What we do in here in ANOVA, as the name indicates, we compare variances. So we calculate two variances and then use them to test the equality of means. So remember, here we are comparing variances, but in the hypothesis testing we are using means. The first one is based on the individual sample variances, which we call the variance within S squared W, which is a measure of the natural variability of the system. The second one is based on the variability of the means, which we will call the variance between S square B, which contains the natural variability and the variability due to differences between the treatments. We set the hypothesis for more than two means like this. The null is that mu1 is equal to mu2 and mu3, and alternative is that at least one of these means is different. And obviously this will be, the condition will be true if mu1 is not equal to rest of them. Then it will be true if mu2 differs or mu3 differs. So at least one of them should differ in order to have the this condition to be true, and in order to reject the null hypothesis. If the null hypothesis is correct, then the this between variance and within variance will be of similar size. But if the alternative hypothesis is correct, then the between variance S square B will be larger than S square W. S square B is actually measuring the treatment effect, the variation between the means of various treatments. Whereas this S square within is the variance for each experimental unit or each observation from its own mean within each treatment, and we do that for the all of the treatments. So variability within those observations or experimental units are the replicates. Replicates are the experimental units getting the same treatments. So that variability should be less than the variability due to the treatment effect, that is the variability between the means of various treatments. Let's go over with some basic concepts. Treatment: the circumstances created to test the hypothesis. Experimental unit: the smallest unit to which the treatment is applied, be it individuals, be it animals or plants, which are getting the same treatments. They are called as the replicates. So the experimental units receiving the same treatments are replications. Suppose here we have three treatments, I is equal to 3. We put this variable I that keeps track of the treatments, and j keeps track of the replications. So here we have 3 treatments versus 5 replications. I just showed them with these different colors. Blue, one treatment, these are the replicates for the other, and the red ones are the replicates for the third treatment. So I runs on the treatments like this. I goes like this. I is equal to 1, first treatment, second and third. J goes here, So this is the first replicate within this first treatment. So its index is 1 1, this is 1 2, 1 3, and so on. Same way here, this gentleman is 2 1, the first replicate within the second treatment, this is the second, and so on. So all of them which are getting the same treatment, they are replicates with respect to each other. Replicates are represented by small letter n. Sometimes we use small letter r for the replicates. We can represent any observation as yij, the intersection between I and j. So for example here, as I said, I is equal to 1, j is equal to 1, this gentleman is I is equal to 3 and j is equal to 5. So these are our observations. Y bar I dot, that is the treatment mean. So this is, for example, if I is equal to 1, dot means that we get this mean for all over these replicates in this J. So I can be 1, for example, as we said that this one is the I is equal to 1, this is I is equal to 2, this is I is equal to 3. Y bar dot dot is the grand mean. So that is the mean which we obtained from using all those 15 experimental units. Here we see, for example, 4 means, and supposedly these means, they look like similar. This gentleman seems like different, and we get the grand mean like this. So here is our grand mean, and then we can calculate the deviations of these individual means from the grand mean like this. So for example, mu1 is here, that is the effect of this treatment one. So we assume that this difference between mu1 from the grand mean is actually because of this treatment effect. Tau 1 here represents the treatment 1. Same way mu2 under the effect of tau 2, and mu3 varies less under the effect of tau 3. Tau is representing treatments here, and treatment number 4 affects more this mu4, so that's a little bit far off from the grand mean. So we calculate those deviations of these treatment means from the grand mean, and then we calculate this variance between these treatments. Before we go deep into this, let's understand the statistical modeling. We did that before very early in the classes, and I said we will get back to it. So here it is. We see it again. So any observation is actually a product of the mean, and then there is some error in it or deviation in it from the mean which we record. So for any observation by I, there is an expected score for this. For example, in the class weight data, if our expectation was, or the mean we believe for the whole class is 50, so anybody having a mean greater than that or less than that, we can model this thing with simple mean here in this equation. This kind of scenario, we call it as linear model or simple linear model. We have a linear relationship between the things, and there is a plus sign in between them. So EY plus error expected, this number or this observation should be equal to expected value. It should have been 50, and let's prove this with some example, and we get this. Again, we can say that this observation has a component coming from the mean. Expected or expectation or mean sometimes use the similar way, and there is the deviation above that mean. So suppose the mean which we expect here is 50, and observation number 1 is 55, the deviation is 5. So in the model we can write 50 plus 5, and same way this second observation was, the score was 50, deviation recorded was 0, and third one is 45, the deviation is -5. Now we want to get the average of those deviations, but before we do that we need to do the sum. So when you do sum of those deviations, this becomes 0. So what we do is we square them, so then we add them up. So this is the sum of those squared deviations, or what we call sum of squares. Sum of squares. We'll use that in ANOVA, this term, sum of squares. Mean of those squared deviations, if we take the average of this thing, squared deviations, and divided by the sample size, how many replicates we do have here, that thing is the variance. And we can also call it mean square, sum of square, and sum of square divided by replicates or sample size, or how many numbers which you are using to calculate those sum of squares. And in case if it's a sample, what we do is n minus 1, so we divide it by degrees of freedom, and we call it as mean square, sum of square and mean square. These terms will be used a lot in the analysis of variance. Again we repeat, so yij is the any observation, and y bar I dot is the treatment mean, and y bar dot dot is the grand mean. So we calculate the deviation for each observation from the grand mean like this, and we add all of them, all the deviations for all observations from the grand mean, and this is our total sum of squares, or total sum of squared deviations, what we call TSS, sum of squares, total sum of squares. This total sum of square is coming from two things. So each observation varies from its mean as well, yij minus y bar I dot. We do that for all these replicates, and we calculate those deviations, one for each of the experimental units or each of these observations. So we will calculate those 15 deviations for these 15 observations, each individual compared with its own mean, this thing, and then we sum them up. So this is sum over yij minus yi dot, y bar actually, the treatment mean, and then we square that. So this is the sum of squares, and we call it as a within sum of square, within each treatment, sum of square within SSW. We also call it as sum of square error, because we don't want those individual observations to vary much within the group, because if they vary much within the group, then when we compare across these groups, this variation will be taking much control of this experiment, and our treatment effect will be it will be hard to get this treatment effect. So that's the crux of this ANOVA actually. So we want the across the treatment, which is the second form of this sum of squares. So that is how each of those treatment means y bar I dot minus y bar dot dot. So how each treatment mean varies from the grand mean. So that is our the third form of this sum of squares. We call it as sum of square treatments, or sum of square between, sum of square between treatments actually, SSBs, or sum of square between.